Hello and welcome to the Computational Storage, how do NVMe and SNIA computational storage work together. I am Bill Martin. I am the SNIA Technical Council co-chair. I'm also the editor for the SNIA computational storage documents, as well as one of the co-chairs of the NVMe computational programs task group. I represent Samsung on SSDIO standards throughout the SSD standards community. I am going to be talking, as the title says here, on how the NVMe and SNIA computational storage models work together. I would like to start by inviting you, if you have not already viewed them, to take a brief break from this and view the presentation done by Stephen Bates and Kim Malone for this conference called NVMe Computational Storage, and also the presentation by Scott Shadley and Jason Mulgard, also at this conference, related to the SNIA computational storage technical work group status and what's being done there. Each of those will give you a more in-depth description of the models that I'm going to be talking about today, but I will give you a brief overview so you can listen to this alone, but if you have a chance, go listen to those as well. With that, the agenda for today is to start with an overview of the SNIA model, proceed to an overview of the NVMe model, and then look at the mapping between NVMe and SNIA, and finally a summary of what we have seen. So with that, I'd like to dive into the SNIA computational storage architecture model. The SNIA computational storage architecture provides for three different broad models. I'll go over those, each one now, and then we'll dig into the details of what's within one of those models. So the first of these on the left side here is the computational storage processor. The computational storage processor does not have any device storage actually on it, and it relies on communication with device storage that it is associated with on the same fabric, relying on peer-to-peer connection to move data between that storage and the computational storage processor. The next of these is computational storage drive. The computational storage drive is like the processor, but it has device storage on the computational storage drive. So it has computation and it has device storage all within a single system. The third is the computational storage array. The computational storage array is similar to the drive, except it has multiple storage devices connected to it, and it has an array controller to present all of those devices as if they are a single device to the host. The computational storage array could be made up of computation plus storage devices, or it may use this computation on a set of computational storage devices that are connected to that array controller. In any rate, all of the compute and all of the storage is presented to the host as if it was a single computational storage device with virtual connections to additional functionality. With all of that said, today I'm going to focus on just the computational storage drive. This is because this is the SNIA model that most closely represents the NVMe model, which is defining a computational programs architecture for a device that has device storage and compute all in a single device. With that, I'd like to move into what are the architectural models, the architectural elements for a computational storage drive. So within the computational storage drive, there is a computational storage engine. This is the hardware, virtual or physical, that is going to be used to perform the compute. Within the computational storage engine, there is a computational storage engine environment. This engine environment may be a Linux kernel that is capable of running on a CPU. This could be a processor that is capable of running Docker packets and able to process those, or it could be a virtual environment that is associated with an FPGA or an ASIC. Next, we have the resource repository. The resource repository is a location on the computational storage drive that is where computational storage functions and computational storage engine environments reside. These may be downloaded or they may be preloaded. Next, we have the function data memory. The function data memory is the area that contains memory that is able to be used by the computational storage function as input, as scratch area, as output. Within that function data memory, there is an area that is called allocated function data memory. This allows the host to allocate specific function data memory for a specific computational storage function. This allows for isolation of what a given function does, but that allocated function data memory can also be used by multiple computational storage functions so that you could have a single function that takes input from that function data memory, puts output data back into the function data memory, and then another computational storage function that works on the output from the first function and then puts its output also back into that allocated function data memory. Finally, the next major important part of this is that there is device storage here. Data can be moved from device storage into the allocated function data memory, and from the allocated function data memory into device storage. The model in SNIA allows for a computational storage function to directly operate on device data in the device storage. This, as we come later, will be something that is a difference between the broad scope of the SNIA architectural model and the NVMe model. Next, let's look at the NVMe computational storage architecture components. Within the NVMe architecture, we have the compute namespaces. The compute namespaces are made up of one or more compute engines, and they have an area for programs to be stored. The programs that are stored in each compute namespace are able to operate on data in what is called the subsystem local memory. This includes program input and program output. It can also be used as scratchpad memory if need be, or if defined by a particular program. Next, we have the subsystem local memory that I've already talked about. This is where data is operated on. And in our next slide, we'll talk about how that is broken up into areas that allow for isolation between the programs. Finally, we have the NVMe namespaces. Now, this is a generalized term to talk about non-volatile memory namespaces. This is where the persistent storage of data occurs. These namespaces may be NVM, which is traditional block storage. They may be zoned namespaces, which is zoned storage, or they may be key value namespaces. There is nothing that precludes or prevents any of these three defined types of persistent storage namespaces from being used in conjunction with the compute. So correlation of SNIA and NVMe terms. I'll briefly go over these here, and on the next slide, I will show you graphically how they relate. So SNIA term, computational storage engine. This is equivalent to the compute engine that is used in a compute namespace. The computational storage engine environment, in NVMe, this is virtual and therefore it's not defined. The resource repository in the SNIA model contains downloaded CSFs and preloaded CSFs. It also contains downloaded CSEEs and preloaded CSEEs. In NVMe, we have the concept of programs. So one of the translations you have to make is between functions in SNIA and programs in NVMe. The two are equivalent. Programs in NVMe may be downloaded or device defined, which means that they are preloaded. However, one of the differences here is that the programs in NVMe are each associated with a given compute namespace as opposed to a global repository. This is a minor difference in architectural usage of the terms that does not really affect how these two models interrelate with each other. Next, we have the function data memory in SNIA. This is identical to the subsystem local memory that is defined in NVMe. Then within that function data memory, we have allocated function data memory in SNIA. In NVMe, we have an area that is called a memory range set. Finally, we have device storage in SNIA. This is identical to the NVM namespaces within NVMe. So taking these two models, putting them side by side, how do these things stack up and work together? So first off, we have the fact that the computational storage engine is equivalent to the compute namespace, which is a namespace that contains one or more physical or logical compute engines. Next, we have the CSFs that are defined in SNIA. These correlate to the programs that are in each compute namespace. Now, as I mentioned on the previous slide, the downloaded programs in NVMe are downloaded into the compute namespace as opposed to being downloaded into a global resource repository for the entire computational storage device. So that is a minor difference. One of the other differences, you'll remember that I said before that the CSEE is a logical function. The device-defined programs are in essence part of the virtual CSEE that when you instantiate a compute namespace, you automatically have any device-defined or preloaded programs associated with that namespace. There is not a concept of preloaded programs being in the resource repository that are then moved by a host application from that resource repository into the compute namespace. So some minor differences there, but it's differences that are not impacting how the models work together per se. So next we have the function data memory. As stated on the previous slide, the function data memory correlates very well with the subsystem local memory being defined in NVMe. So there's no real concerns over that mapping. Additionally, the allocated function data memory correlates with the memory range sets. For more understanding of how the memory range sets are defined and used, you may want to, as I said earlier, look at the NVMe computational storage presentation done by Stephen Bates and Kim Malone. But basically, the one concept here that is important to note is a memory range set is actually not created in the subsystem local memory. The memory range set is defined within the compute namespace. So while the diagram in SNIA shows the AFDM in a separate block within NVMe, you could, in essence, look at AFDM being a mapping that is done within the computational storage engine to a particular set of memory addresses within the subsystem local memory. So next we have device storage. The device storage in SNIA is mapped directly to the NVM namespaces within NVMe. So in summary, SNIA is a general architectural model for computational storage. It is not specific to any particular protocol layer. In NVMe, the computational programs is a specific I/O command set for computational programs. It is specific to the NVMe protocol. Within SNIA, you have flexibility for a variety of protocols, while the NVMe computational programs command set is specific for the NVMe protocol. So there are, as I mentioned, two presentations already, the latest efforts in the SNIA Computational Storage Technical Work Group that is being done by Scott and Jason, the NVMe Computational Storage, an update on the standard being done by Stephen and Kim, and finally, Programming with Computational Storage being done by Oscar Pinto. Programming with Computational Storage will show you the SNIA API that is being developed to give you an application programming interface so that your application with the appropriate library can communicate with a computational storage device built within any protocol that is out there that is supporting computational storage. So with that, I would invite you to both join SNIA and NVMe in the standardization effort so that you can be aware of the changes as they develop, and also so that you can help define and develop computational storage within the industry. So thank you for watching. Please take a moment to rate this session. Your feedback is very important to us. We do look at it. We are very interested in it. Thank you very much.